Hi, this is Anna Doblas again, recording another video for you guys. I really hope that you like them. The video that I would like to present to you is one of our latest work. It's about an automatic algorithm to reconstruct quantitative phase images in digital holographic microscopes. This work has been recently published in Applied Optics, and it has been chosen as an editor pick, so I really hope that you like them. So first of all, if you are just starting in the topic, you might not know what is the meaning of digital holographic microscopy. Why are we using this technique? So this is a microscopy technique, and the main difference with respect fluorescent imaging techniques is that the samples, you don't need to state them. So that's what is called a label-free technique. And what we are getting is we are getting the complex information of the sample, we are getting the amplitude and the phase information of the sample. So the main advantage is because we have the 3D, the kind of like the 3D information, the object and the sample, we can numerically reconstruct at any plane. So that means like, even if your sample is out of focus, you can focus it numerically without losing any resolution. And that's really useful for practical tracking, like digital holographic microscope. They have been used to kind of like analyze the motility of sparse samples, and that is because the spurs keep moving within the field of view, but even though that they become out of focus, you can numerically focus later. One within the DHM systems, one of them is called the off-axis DHM systems. And what that means is you only need one image to have the 3D information of the amplitude and the phase. And that becomes really handy for live imaging applications. So these are the videos of one of the commercial DHM systems, but where is used DHM system is for live cell imaging, analysis of cell and tissues. Several groups have been working about disease diagnosis and screening. NanoLife, the commercial NanoLife system, they have used the system for drug discovery. Since it's in vivo, you can really see if when you apply a drug into your biological system, what is the response, and obviously about particle tracking due to the numerical focusing capability. So the main idea about DHM is an interferometer. So it's nothing more than an optical interferometer. So the more basic optical interferometer that you can think about, it's a Mach Zehnder interferometer. So the light from the laser gets divided into two beams by a beam splitter. So we're gonna have the object and the reference beam. Just because you want to have like a wider area that they get the overlay, you might want to kind of like expand your reference beam. And then in your object arm, what you have is a microscope. So you have a microscope objective lens, an infinity corrected microscope objective lens, that it creates the image of your sample that you're gonna put at a working distance from it at the infinity. But since we don't have access to the infinity, you insert a tube lens so that the image is generated at each back focal plane or its image focal plane. And that's the position that you want to place the sensor if you want to have in focus images. But if you don't care about that one, you just might put your sensor in another axial position and later use numerical focusing algorithms to focus your sample. But at the end of the day, that's a microscope. So what that means is the amplitude scattered by the object is just the 2D convolution of the complex amplitude distribution of your object with the point spread function of your system, which is not anymore like a replica of the Fourier transform of your pupil of the microscope. And since it's an interferometer, we are getting the square modulus with the reference And that's what we're gonna call the hologram. So the hologram, it has like 4 different terms. The 2 first terms are the terms related with the intensity of the object and the reference. And those terms, they don't contain any information about phase imaging. But these 2 additional terms that if you can realize there are one conjugated from the other, those are the terms that we care. And in particular, the term that we care is the complex amplitude distribution of the object. If you can get the without the conjugation or with the conjugate operator, that's okay. We can handle both of them. But you see, like the term that we want, it's mixed with another different term, right? So how are we gonna work it out? So in off-axis DHM systems, if you make the Fourier transform, you're gonna realize that these terms, they are placed in different positions in the Fourier domain. So for example, the DC term, which is just the Fourier transform of the intensity of the object and the reference, it's always placed at the middle of the Fourier transform. While the other 2 terms, they call the +1 term and the -1 term, are placed symmetrically with it. And in a off-axis DHM system, there is no overlapping with them. That's the key. Off-axis DHM systems are those systems where it is the spectrum of the recorded hologram, we can distinguish the 3 terms. So how are we going to reconstruct? Because what we want to get is the complex amplitude information of the object. And we cannot do it in the space domain, but in the Fourier domain, we know that it's going to be this term. So how are we going to do it? That's easy. It's get placed in a different position, so we can filter it out. We can select a mask, only selecting the +1 term, blocking the DC term and the minus term. We know that it's not centered in the Fourier domain, but that's okay. We know that this is because there is a reference, the angle with the object and the reference. So we can compensate it back. We can center it in the Fourier domain. And later, our sensor is in the image plane of the microscope. So we just need to come back to the space domain and get the magnitude or the angle to have amplitude or phase contrast images. This step, which is like the one for compensating, it's simple to understand, but if we don't perform it with enough accuracy, we're gonna have distorted phase images. So for example, we want to reconstruct to center it. How we're gonna do it is we don't do it in the Fourier domain. What we do is our filter width. So we have here the filter spectrum, and then we compute we go to the space domain, and that complex amplitude information now it gets multiplied with a digital reference wave. So this digital reference wave is just a replica of the optical of the physical reference wave, but what we need to know is the angle. What is the angle with the object and the reference? And assuming that our reference beam is a plane wave, for the angle, the only thing that we need to know is really the positions of the maximum peak. So if our reference beam is a plane wave, what that means is Fourier transform, it's a delta, a Dirac delta function. So the center needs to be maximum. So we just need to know where is the center, the maximum position of the +1 term along the X and Y axis, and then the wavelength, how many pixels we have, and the size of the pinholes and of the pixels. But roughly, all this information is already well known. So we can generate our digital reference wave multiply by the space distribution of the filter hologram spectrum. And now we estimate the phase doing the inverse of the tangent of the imaginary part versus the real part. And that's how we do it. But what I was saying, that estimating the maximum peak of the +1 term, it's well known. If your reference is a plane wave, that is true, but there is a problem. The ideal case that we are assuming is our maximum peak, or the frequency of our plane wave, coincides with a maximum peak and with an integer value. So that means it's so easy to determine. But there's gonna be cases where the angle of interference does not coincide with the integer value of a pixel. So we're gonna deal with this kind of situation experimentally. So we can estimate the maximum, and the code can give us one of these two values, but these are not good enough for having accurate reconstruction. So we need to find out a method where we can estimate non-integer values and give us accurate quantitative phase imaging. And this is like an example, like this image. We are seeing here that both of them, the values that we are using is definitely a non-integer value, but this value, it gives us a uniform background, minimum phase distortions. Yeah, there are here a couple of phase distortion, but that's related with the edges of the sample. But if you see, for example, on the other side, on the right side, we have distortions due to the incorrect use of the Umax and Vmax values, and it's roughly 1 pixel off. So definitely we want to have so many accuracy to estimate what is the correct value of Umax and Vmax. So there are different algorithms. We are not the only ones working here in this topic. There are other people that they have worked. For example, here they published a work where they were selecting the Umax Vmax values as the center of the +1 term, using like centroid mass approaches. The other approach was proposed by our colleague Carlos Trujillo, and what they were using for loops. So they have double nested for loops, and they will keep changing the values until they will say, oh, this is a good enough, that's the best reconstruction that we can do it. But if you can think about it, that's gonna become time consuming. So what we are doing is, we are not using for loop, but we are definitely basing our approach in what Trujillo mentioned, and is that the best reconstructed phase image is the one that it has minimum phase jump. So you see these fringes, sawtooth, the sawtooth fringes around, like when we see like changes of black and white, that means that there is a phase wrapping. Like your phase value was going up and then it kind of wrap down and keep increasing. So unless that your sample is thick, but most of the samples are thin enough that we should not experience any phase wrapping. So we can kind of estimate what is the best reconstruction in the one that we have the less number of pixels that they have experienced phase wrapping. And how we're gonna measure that phase wrapping? We're gonna measure it just with a binary image. So our reconstructed phase image through the method is gonna get binarized, and we're gonna count how many pixels. Ideally, we don't want to have any phase wrapping. All the pixels that we have from the image needs to be 1, right? So if we subtract the binary pixel with the total number of pixels, that needs to be 0. But since we may have some kind of phase wrapping within the edges of the sample, we're gonna count how many we have, and we're gonna keep changing the values of Umax, Vmax until we get the minimum number of phase wrapping. And this is like an example where how this is gonna work. So our approach is not gonna use double for loops, it's gonna minimize a cost function. And the cost function is roughly tracking how many pixels of the binary image are equal to 1. So what we need to do? All right, so the input of our approach is only the hologram, the wavelength of the light that you are using, and then the pixel size. These are the 3 input parameters that you need to use. Then it goes to a module that is related with the spatial filtering. So you make the Fourier transform of your object. The program computes the values of the position of the +1 center, which that's gonna get used as a seed for the minimization. And it's gonna create a mask to filter out the +1 term and coming back to the space domain. If you want to do amplitude imaging, that's good enough. You don't need to go to the other modules. But since this is for quantitative phase imaging, we need to compensate in the best way as possible that we have right now the interference angle. So we're gonna set up the function, like we're gonna set up the parameters for our cost function, the tolerance and the number of iterations that we're gonna use, and then the seed values, we're gonna start updating it through the minimization until we have the best. So every time that we are estimating a new value of the Umax and Vmax, we are compensating, we are tracking how many pixels we have, and that's gonna be the value of the cost function. We're gonna see what it was the value compared with before, have we improved, yes or no? And if it's no, we keep changing. If it's yes, we keep changing until there is the convergence. And here is like some kind of result that we're gonna have with the binary image through the const function for every step. And once we have said yes, we have arrived to the minimum const function, then that's the moment where we're gonna compensate, we're gonna create that new digital reference wave and compensate with our space domain, the filtering of the +1 term in the space domain, and compute the phase reconstruction. So let me show here some examples. So here we have three examples, three different two biological samples, one calibrated target, the use of target, and we are getting compared with the three methods. The for loops, the nested loops method, the centroid method, and then our method. So we're gonna see that the results of our method are the one that it has less, they are the best compared, like we have less phase wrapping. It looks like our samples are better compensating. It's different, like every sample, like for example, for the use of target, the centroid is not doing really bad, but if you can see here for the glioblastoma, it's failing. Well, the nested loop, it's doing a pretty good job with the glioblastoma cells. So every sample, it kind of depends how the algorithms are performing, but our proposed method overall gives us a more stable and robust performance across different type of samples. And obviously this is completely qualitative, but what it's gonna tell us about the quantitative. So the three different images that I have shown, they have different values, and that's important in terms of the processing time. Our method, even though it's less, it's like 1.6 seconds the least time, but if we increase double the size of the image, it becomes to 3.3 or 2.6 seconds. That is pretty fast. It's even faster than the centroid method, and definitely so much faster than the the nested for loop methods. They give us different values. If you see the values, they are not like a huge difference between them, but still it's a pretty good difference, and that's why it makes us the result so like different and our method more accurate. The accuracy approach, this is telling us how many, we estimate the accuracy based on how many pixels now they are equal to 1 in the binary image and how many pixels we are not. So that's how we measure the accuracy. So our method, it's high, the accuracy is the least is 95%. So that's a pretty good accuracy. The other methods are definitely providing less accuracy for estimating the result. So here, just to finalize, we have proposed an affirmative method for reconstructed quantitative phase imaging of axis DHM system. The DHM system needs to operate in telecentric regime, and that means is the of the +1 peak needs to be a maximum, otherwise it's not gonna work out. And we only require two input parameters, the wavelength of the source and the pixel size. The hallmark of the approach is it's really accurate. It gives us up to 6 decimal digits of the reference wave. So it gives us a really accurate estimation of the interference angle. It's also really fast. It's 40 times faster than the nested loop approach and 2.3 faster than the centroid-based algorithm. Here we saw that our experimental results, they have minimum or non-phase perturbation, so that's what we really want to have. And we have also tested, so even though I showed results with a Mach-Zehnder interferometer, we tested also with a Michelson interferometer. So it doesn't matter if the sample is transmissive or reflective, as far as the DHM system operates in telecentric regime. it's gonna work out. Currently, we are working in updating the approach, so it's not only working for telecentric, it's working for non-telecentric, and also it's able to focus in your samples automatically. Well, I really hope, well, let me finalize with the acknowledgement. So those are our collaborators, and this work has been funded by University of Memphis, but also this video is part of the educational outreach activity of my NSF career. We want always to thank our research group. This work was mainly performed by Raul Castaneda, but other members of the group have been working out, and always we appreciate the feedback. If you have any question, just let us know. If you visit our website, you're gonna see that we have the GitHub available for you. So we have the Python code and also the MATLAB code, so you can test it out, our method, and just let us know. We are here to support your knowledge in digital holographic microscopy. Bye.